Inverse functions. Before we take a look at inverse functions, we have to know what a one-to-one function is. A function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. In other words, there is no repeat in the range values. Now, the best way to determine if a function is one-to-one would be to have its graph and to apply the horizontal line test. So we say a function f of x is one-to-one if there is no horizontal line that can be drawn that intersects the graph of f of x in more than one point. So previously, our vertical line test said that if there was no vertical line that could be drawn that intersects the graph in more than one point, then we had a function. So now, if there is no horizontal line that can be drawn that intersects the graph in more than one point, we have a one-to-one function. So in this first example, we're going to look at which graphs represent one-to-one functions. So on this graph on the left, I have this upside-down parabola here, and it's definitely a function. It passes the vertical line test, but I can draw a horizontal line that will intersect in more than one place. So this first one is not a one-to-one function. So we're going to say not one-to-one. Now, the second graph here is a function. It does pass the vertical line test, but right in the middle, if I draw a horizontal line, I'm actually going to hit the graph 3 times. So this is also definitely not one-to-one. But finally, the last one is the graph of x cubed, and it is a function. It passes the vertical line test, but it also passes the horizontal line test. I can draw a horizontal line test anywhere, even near the x-axis. I know to the naked eye it doesn't look like it, but I can draw a horizontal line anywhere, and it's only going to intersect the graph one time. So x cubed is a one-to-one function, sometimes abbreviated when writing as just literally the number 1 dash the number. Now let's define inverse functions. Let f of x and g of x be two functions such that both have the property that f of g of x is equal to x and g of f of x is equal to x. Then we say that g of x is the inverse of f of x, and we use the notation g of x equals f, and then it looks like to the power of -1 of x, but we don't read it like that. We read it as f inverse of x. So note that f of x must be one-to-one to have an inverse. So in order for two functions to be inverses, their compositions in both directions have to give us just x. Now my warning about the notation is because it looks like f to the -1 of x, sometimes people think they can rewrite that as 1 over f of x, like they can take that -1 and bring f to the denominator. But that's not true. So this is very specific notation to functions, and it means an inverse. And again, that's how it's read out loud. We don't think about it as to a -1, like a number being raised to the -1. It's different when it's the name of a function being raised to the -1. We don't consider it that. We consider it an inverse. In this example, we want to show that f of x equals the cube root of the quantity x minus 2, and g of x equals x cubed plus 2 are inverses by showing f of g of x is equal to x and g of f of x is equal to x. So we'll start by considering f of g of x. So we're going to go ahead and perform the composition f of the quantity x cubed plus 2, which means that x cubed plus 2 is going to replace the x in the f of x function. So we're going to end up with the cube root of the quantity x cubed plus 2 and then minus 2. So we substituted in x cubed plus 2 in for x. Well, now underneath the cube root symbol, the plus 2 and the minus 2 are going to cancel out. So what I have is the cube root of x cubed, which is just x. And if we need a reminder of why, we technically have x cubed to the 1/3 power. So the cube root becomes the rational exponent 1/3, and 3 times 1/3 gives us 1. So that's why we end up with just x. So we have shown that one of the compositions equals x, but we have to show the other one does as well. They both have to yield just x. So now let's go ahead and think about what is g composed with f of x. So that's g of the cube root of the quantity x minus 2. So I'm substituting the cube root of the quantity x minus 2 into the x in the g of x function. So the cube root of the quantity x minus 2 cubed plus 2. And now the cube root and the cubed power are going to cancel because of the same reason we said earlier, 1/3 and 3 in the exponent. And now what I have is x minus 2 plus 2. And the x minus 2 and the plus 2, the minus 2 plus 2 are gone, leaving us with just x. So we have shown that f of g of x equals x, and g of f of x also equals x. Let's move on to finding the inverse of a function. We'll start with the numerical understanding. Numerically, if x comma y is a point on f, then y comma x is a point on f inverse of x. So we literally switch the x value and the y value to get a point on its inverse. So graphically, what that means is that f of x and f inverse of x are mirrored or reflected over the line y equals x. Now for this example, given the graph of f below, sketch the graph of f inverse of x on the same plane. So here for part A, this is going to be my graph of f of x. And I'm going to start by just labeling some of the values on this graph with their coordinate points. So I have 0, 1 is one of the points. I have 1, 2. I have 2, 4. I'm trying to pick the points that go through integers, but I'm also going to go ahead and choose -1, 1/2 here. Because now on the graph of its inverse, I'm going to go ahead and take the x and y values of those points and switch them. So instead of -1, 1/2, I'm going to plot 1/2, -1. And instead of 0, 1, I'm going to plot 1, 0. Instead of 1, 2, I'm going to plot 2, 1. And instead of 2, 4, I'm going to plot 4, 2. And so now to help sort of guide my graph and connecting the points together accurately, I want to think about the fact that these two graphs are going to have to mirror image or reflect over the line y equals x. So I'm going to draw the graph of y equals x as a dotted line. So remember, it passes through the origin with a slope of 1. So I've constructed the graph of y equals x, and that's just as a way to help guide me that my inverse should be a reflection over that line of the graph of f. So I'm going to go ahead and connect these values here as best I can to make it look like it is a mirror image. So the point should be the same distance away from that line y equals x. And then notice that on the graph of f, it looks like I have a horizontal asymptote. It looks like my curve is approaching the x-axis. Well, that means on f inverse, now my points look like they are approaching the y-axis. So this would be a sketch of f inverse for part A. In part B, I have here the graph of f, and this time, instead of starting with picking points, I'm going to start by sketching that line y equals x. So it's going to pass through 0, 0, and 1, 1, and 2, 2, and I'm drawing it as a dotted line through y equals x. And so now I want to think about, well, what would the inverse graph look like, the reflection over the line y equals x. So I'm going to take this piece at a time. So I'm going to first go ahead and take this little piece here and think about reflecting it over the line y equals x. So I'm going to go ahead and draw this little curve here. Notice that they meet at 2, 2, because you can't flip 2, 2. They're x and y and x are the same. And then I'm going to continue on with this piece here, and I'm going to go ahead and try to reflect it over the line y equals x. I'm going to try to make them equidistant as best I can, and then I'm going to continue down here in quadrant 3 doing the same thing. So taking the mirror image of the line y equals x. And then finally that little piece there. So they intertwine with each other. So I would reflect each piece. If it was below y equals x, it would flip on top of it. If I had a piece above y equals x, it would flip on the other side of y equals x. So this is my graph, a sketch of f inverse. One final thing to notice about both of these original functions f is that they were 1 to 1. So we would not have been able to graph their inverse if they did not pass the horizontal line test to begin with. So that is definitely something we want to remember about finding the inverse. Now let's move on to finding the inverse of a function, but this time analytically. In this example, we're asked to find the inverse of f of x equals the square root of x minus 3 and graph both f of x and f inverse of x on the same xy plane. Well, I'm actually going to start with first graphing f of x so that we can guarantee that we have a 1 to 1 function. So f of x is the square root of x graph shifted down 3 units. So this minus 3 is going to take us down 3 units. Normally I would start at 0, 0. So then this time I will start at 0, negative 3. And then I'll pass through the point 1, negative 2 and 4, negative 1. So connecting those points together, I have the graph of f of x, and it does pass the horizontal line test. This is a 1 to 1 function. So we can go ahead and find its inverse, and the steps for doing so analytically are here. So the first thing we'll do is replace f of x with y. So we're going to start by writing y equals the square root of x minus 3. The second step is to switch x's and y. So everywhere there is a y, we're going to switch it to become an x, and everywhere there's an x, we're going to switch it to become a y. That will leave us with x equals the square root of y minus 3. Step 3 is to now solve for y, because now y is buried inside of the right side of the equation, so I need to solve for it to get it by itself. I'm going to go ahead and add the 3 to the other side. So x plus 3 equals the square root of y. And then to get rid of the square root, I'm going to square both sides. So I have the quantity x plus 3 squared equals y. The last step is if you solve for y, which we did, we're done, replace y with f inverse of x. So now f inverse of x equals this quantity x plus 3 squared. But I'm going to write it so that f inverse of x goes first. So f inverse of x equals x plus 3 as a quantity squared. And now let's go ahead and think about graphing that inverse function. That's the last part. Well, x plus 3 squared as a quantity squared is going to take our parabola and shift it left 3 units. Normally, the parabola starts at 0, 0, so our vertex is going to be moved over to negative 3, 0. So it looks good so far because on f of x, we pass through 0, negative 3. So on the inverse, I pass through negative 3, 0. But our parabola is going to exist on the left and right side of negative 3. So I'm going to go ahead and sketch the full parabola, and then we'll go ahead and sort of think about why I have to erase one side of my full parabola here. Well, if I think about the reflection over the line y equals x of f of x, the reflection of this square root function is not going to be both parts of this full parabola. So we already said negative 3, 0 is going to work. So if I think about 1, negative 2, that's going to pass through negative 2, 1. So I'm going to only have the right side of this parabola stick around as my f inverse graph. So the other side is gone. The other side is gone. I'm going to go ahead and erase it. So only the right side of the parabola is my inverse function. So that means I have to come back over to the equation and I have to restrict the inverse's domain. Because this full parabola isn't the inverse of the square root function, only half of it is. So only the part where x values are greater than or equal to negative 3. So I had to include a domain restriction on my graph of f. In this next example, we're told that to convert from x degrees Celsius to y degrees Fahrenheit, we use the formula f of x equals 9 over 5 times x plus 32. Find the inverse function, if it exists, and explain its meaning. So this function, if we substitute in a value of x that's in degrees Celsius, what will come out as y, because remember y equals f of x, what will come out as y is the conversion to degrees Fahrenheit. Now we want to go ahead and find the inverse, if it exists. So the only way we can find the inverse is if the function is 1 to 1. Now 9 over 5 times x plus 32 is a linear function. So since I have a linear function, as long as it's not a horizontal line, which it's not, I am going to have a 1-to-1 function. So any line, even with positive or negative slope, as long as it doesn't have constant slope, will be a 1-to-1 function. So that means that I can go about finding its inverse analytically. So checking whether it's 1-to-1 is kind of like a step 0. So we definitely want to make sure that we've convinced ourselves either graphically or just by actually drawing the graph or knowing about the graph of the function that it is 1-to-1 before we proceed. So now that we know it is 1-to-1, I will go ahead and move on to step 1, which is to let f of x equal y. So y is equal to 9 over 5 times x plus 32. And then the second step is to switch the x's and y's. So y becomes an x. So I have x equals 9 over 5 times y plus 32. And then I go ahead and try to solve for y now that it's on the other side of the equation. I'm going to subtract 32 to the other side. So x minus 32 equals 9 over 5 times y. And then I have to get y by itself. And while we could think about it as dividing by 9 over 5, the better way to think about getting rid of this fraction 9 over 5 is by multiplying by its reciprocal on both sides. We're going to multiply by 5 over 9 on both sides. So we have 5 over 9 times the quantity x minus 32 is going to equal just y. So the last step here would be to replace y with the f inverse notation. So we have f inverse of x is equal to 5 over 9 times the quantity x minus 32. So this is the inverse function. And the last part is to explain its meaning. Well, the original function converted us from x degrees Celsius to y degrees Fahrenheit. but then we went ahead and switched their places. So now x represents degrees Fahrenheit. So when I substitute in values of x, it's in degrees Fahrenheit, and what will come out is degrees Celsius. So what this represents is a conversion, right? It's going to convert from degrees Fahrenheit, so that is x values, to degrees Celsius. That's our new y values, our f inverse of x values. So that's what it's going to do. It's going to convert from degrees Fahrenheit, which is x, to degrees Celsius in y. In this example, we're told to start by graphing y equals the quantity x plus 2 squared minus 3 and find a domain where the function is 1-to-1 and increasing. Then find the inverse restricted to that domain and graph the inverse. So let's start by graphing. Let's recognize that our parent function is y equals x squared, and our translations are that everything's going to move to the left 2 and down 3. So I'm going to go ahead and construct an xy plane here. And my original parabola shape is going to head to the left 2 units and down 3 units. So far I'm just going to label the tick marks that are relevant to my current graph. So my vertex is going to pass through -2, -3 down here. And then I'll go ahead and start to construct my shape of my parabola. That's not right. Okay, so it's just a rough sketch of y equals the quantity x plus 2 squared minus 3. And I want to find a domain where the function is 1-to-1 and increasing. So the part of this graph that is increasing is going to be the right-hand side, the part to the right of -2, the right side of the vertex. That part's increasing. Because I could choose either the right side or the left side as individual sides. Those would be 1-to-1. They would pass the horizontal line test. So that's why this problem is being a little more specific. Pick the part that's increasing. So I'm going to go ahead and erase the other side, because this right-hand side is going to be the part that I'm going to find an inverse for. So now I'm going to go ahead and say y equals the quantity x plus 2 squared minus 3. This is going to be restricted when x values are greater than or equal to -2. Let's go ahead and find its inverse. Well, we don't have to replace y with f inverse. It already is y. So now we just change the y to an x and the x to a y. So I have x equals y plus 2 squared minus 3. And then we'll solve for y. So we'll add the 3 to the other side. X plus 3 equals the quantity of y plus 2 squared. Now, to get rid of the squared, I'm going to need to take the square root of both sides, but what's going to happen is I'm going to get plus or minus the square root of the quantity x plus 3 equals y plus 2, and then I'll subtract the 2 from the other side and leave it in front, so I have -2 plus or minus the square root of x plus 3 is equal to y. Well, y is the inverse, and we can't have two different functions be the inverse. So we created two different functions here. We created -2 plus the square root of x plus 3, and -2 minus the square root of x plus 3. So the only difference here is that the square root of x plus 3 here on the top one, the positive one, doesn't have a reflection over the x-axis, and the second one does. Well, we have to graph the inverse anyway, so we'll be able to determine which one of these the equation is. So let's go ahead and remember that the inverse is going to reflect over the line y equals x. So I'll sketch the line y equals x. So here we have it, and what we can do is take our coordinate points and switch the x and y values to graph the inverse. So I have the point -2, -3, so if I switch x and y, I'll have -3, -2, and then -1, -2
will become -2, -1. So I'll just draw those 2 points and then recognize I'm just drawing a reflection over the line y equals x. So it's going to look like a square root function without a reflection. So there is a shift to the left 3 and down 2 of a square root function, but it doesn't reflect over the x-axis. So it's going to have to be this first version, y equals -2 plus the square root of x plus 3, which has a shift left 3 and down 2. But we don't want the one with a reflection. So it's not the bottom option. We're going to go ahead and say that the top one is f inverse. So here's our inverse function, and we can see that the domain that it is restricted to starts at the x value -3. So this is our inverse function, and it's defined when x is greater than or equal to -3.
With the graphs, we have already been sort of talking about the domain of an inverse, but let's go ahead and clarify a few concepts. So the domain of f inverse of x. Since the points on f and f inverse are switched, the domain of f is equal to the range of f inverse, and the domain of f inverse is the range of f of x. It all goes back to the concept of the numerical understanding of an inverse, that x and y switch places. So let's now look at an example. In this last example, we're going to find the inverse of f of x equals 2x over the quantity x plus 3. Note that f is 1 to 1, so we don't have to graph it and verify. We're just given that f is 1 to 1. Find the domain and range for both f of x and f inverse of x. So let's start by going ahead and thinking about f of x equals 2x over x plus 3. And before we try to find its inverse, let's think about the domain of f, because I want both the domain and range for both f and f inverse. So for f of x, its domain is going to be everything except -3. So in this case, for this rational function, the only value that I cannot substitute in is going to be -3. So the domain, and I'm going to clarify a little, the domain of f is going to be all x values from -infinity to -3, and -3 to infinity, everything except for -3. Now, technically, I have already found the range of f inverse, because the domain of f is the same as the range of f inverse. And I actually cannot yet find the range of f. So here I'm going to leave range of f, and I'm going to leave it blank for now, because from the equation or the function itself, I cannot determine the range. So I'm going to kind of hold off for now because I don't have that. And then what I'm going to do is I'm going to write down at the bottom, because we don't want to forget this information. Eventually I'm going to want the domain of f inverse and the range of f inverse. Well, I already have the range of f inverse because I have the domain of f. The range of f inverse are all the y values from -infinity to -3 and -3 to infinity. So what we're going to need to do is do all the work to find the inverse function, and then the domain of f inverse we will have, and then that will be the range of f. So now let's actually go through the algebra of finding the inverse function here. So we're going to replace f of x with y. Y equals 2x over x plus 3. And then we're going to switch out the y for an x, and we're going to switch out each x for a y. So 2y over y plus 3. Well, this one's slightly different because now I have two y values involved, and I have to get y equals by itself, just y by itself. So the first thing I'm going to do is I'm going to multiply both sides by y plus 3. So if I multiply by y plus 3, I'm basically clearing my fraction. So the y plus 3 on the right side is gone. And now what I want to do is I want to distribute in this x on the left-hand side. So if I distribute in this x, I'll get x times y plus 3x is equal to 2y. And so now how that helped us is that now I can do some rearranging. I can go ahead and get the 2y on the left side if I subtract it over, and I can subtract over the 3x to the other side. So I'm collecting my terms with y on one side of the equal sign. I have xy minus 2y is equal to negative 3x. So I subtracted and then I subtracted to the other side. Well, the benefit is that now xy minus 2xy, they both have a y in common, and I can factor it out. So my work's going to travel up here now. I'm going to take out a y, and I'm left with x minus 2 left over. So y times the quantity x minus 2 equals negative 3x. And then the last step is get this y by itself. We'll divide by this quantity x minus 2. So I have y equals negative 3x over x minus 2, the quantity x minus 2. So now that y is by itself on one side, I can go ahead and replace y with f inverse. So f inverse of x is negative 3x over x minus 2. So this is my inverse function, and because I actually have the function, I can find its domain. So from a function, I can find the domain. Well, the only problem value is 2. I can't plug a 2 in because that'll make the bottom equal 0. So the domain of f inverse is everything except for 2. So all x values, negative infinity to 2 and 2 to infinity. And because I have the domain of f inverse, that actually gives me the range of f, which I otherwise would not have been able to find unless I had the graph. So I can go ahead and make it y values from negative infinity to 2 and 2 to infinity. Now I just have one final side note, because sometimes students will work through some of these longer inverse problems and they'll get to an answer and they'll say their answer doesn't match the answer key. So I'm going to go ahead and just give you another way to think about this final answer here. So f inverse of x is negative 3x over x minus 2. But remember that a negative that's being multiplied in a quotient like this, we can associate it with the numerator, the denominator, or we can pull it to the outside completely. So we can think about it as negative times 3x over the quantity x minus 2. Or we can distribute this negative to the denominator. So you'll see sometimes 3x over negative x plus 2, or probably more commonly 3x over 2 minus x. So there's basically some different versions you could see, but all of these are exactly the same. So you want to get comfortable knowing when you do have an equivalent equation just manipulated by a negative.